Okay, let's close now. Wait a second, please. Let me set dial. Okay, checking time first. 物语，赵家琪，崔家园，陆一凡，姚如歌，李宗浩 ，Ricky， Jenna， 丁，刘敬成，朱娜，蔡家峰，Maxine。Okay. So last week we tried to introduce the radiation by antennas, and so we take the first thing as the parameter. It's the electric field aperture distribution or illumination. So we set the illumination via from a whole antenna from the aperture. Can be expressed as XA, YA in two-dimensional. Okay. So and we also set the focal distance. SR should be than 2D square or lambda. Okay. And so the parameter D is the longest linear dimension of the aperture or the radiating aperture, and R is the distance from the observation point to the center of the aperture. So the aperture illumination can be expressed in the spherical coordinate system. We expressed as J or lambda times the spherical wave, right? So by R and minus J K to R times H theta. Alright? And H theta phi is this parameter is referred to the form factor, right? So it already determines the pattern of the illumination. So this is the radiated field or the aperture illumination, and if we want to calculate its power density, it should be expressed as R theta phi, alright? And also the absolute value, square of the absolute value divided by intrinsic impedance, alright? So like it, and then it can be further evolution on the equation. Beta note the sphere, R² divided by here is h theta. This way. So this is the periodicity of the radiated beam, and then we take an example for the rectangular aperture. So for a rectangular aperture, we take the area element for an example. And first we set there is a plane. Right, and there is a rectangular aperture. This one. Right, and we set the coordinate system. When we set the coordinate system, this is x. Okay. The y-axis is along this direction, and it propagates along this dimension is L, y, and its length. And along this direction, along the x-axis is Lx is dimension, alright? So because we first here we set as uniform field distribution. So that means the radiation field is uniform over the whole aperture, and it can be said to be node, right? For when the XA is then half of x smaller than half of x, and the xy smaller than minus half ly smaller than half ly also, and of course 0. So this is uniform distribution, a field distribution, and we can get the form factor h y. It can be expressed finally after the evolution j times node p divided by lambda times e minus j k r divided by k r times a sinc function and by Lx c theta cosine phi times sinc again pi ly over lambda c theta cosine this sin theta sin. So when we take we just take the xy plane, take the xy plane over this plane, and if we wanted to get the patterns or the radiation patterns, previously we set the normalized intensity vector, right? Sin theta is related like this one, and it equals the what? The power intensity, alright? And we set the phi equals 0, right, along this look set from the x-axis. So, and the power density, the maximum, right? So it can be expressed as sec square pi per x over lambda sin theta. And when we try to simplify it, like this one, gamma square, and gamma equals Rx over lambda sin theta, like this one. Make it to be more simplified like this one. So, okay, remember this equation. We're gonna get the radiation pattern based on this one, and so because here we can say as a sinc function. So actually, when we want to plot the radiation pattern, it's going to follow the sinc function actually. So I would continue. So here is x-axis. So that is symmetric. Here is the radiation pattern, and because it is normalized, alright, if it is in the normal radiation pattern, it looks like this one. The main beam, this, and the x-axis refers to the gamma, which equals Rx over lambda times sin theta, right? So this is the maximum, and here is 0. So this one is 0 also, dB, and here is minus 30. Example, and the side lobes. This one, alright. Here, this side is symmetric. This one. So, for such a radiation pattern, the first thing we usually get is the half power beam base, alright, and then the non-beam base. So, for this part, for the half power beam base, because we just take because we look at along the x-axis, so the beam base, the half power beam base, corresponds to the 3 dB minus 3 dB, right? So minus 3 dB. So the corresponding beam base is this is the half power beam base, and also the 0. And for such a function, get this, the height of this, the first order side lobe is minus 13.2 dB. 13.2 dB. So for this one, and also for beta x zeta, and so for this is for the x or y plane, and for the x y or zeta plane, x or zeta, for the x or y plane, y or zeta plane, we can also get another beam base. It's the beta y theta, alright? So for such a condition. So for the half power beamwidth, which means if we set the f equals 0.5, which means the sin square Lx over lambda times sin theta and times 0.3 equals 0.5, and we can get the values for these theta over to 0.4 times 4 times L lambda over Lx. So this is for the x. So this is half of that, right? So this is just this is theta 1 and theta 2. So this is just for theta 2, for example, theta 2. And for theta 1, it's the same thing, to be minus 0.44. So the beta x of theta equals the double of that, right? Because here is just half of that. So it equals 0.88 lambda over Lx. This is the beta x of the on the x of theta thing, and on the y of theta plane can also expressed as 0.88 times lambda over Ly. Alright, so it is determined by the aperture or the dimension of the apertures. This is in the unit reading. This one. So here you can see that the beam width, actually this part is corresponding to the beam width, alright, in the x or theta plane and over the x or y plane. So this is the beam width. So this one. So for the uniform, alright. So this is for a uniform aperture distribution. For the uniform aperture distribution, that means over the aperture, its electric field is a constant across the aperture, gives a far field pattern with the narrowest possible beam width. Narrowest possible beam width. Why? Then we introduced another antenna which can a cylindrical reflector, right? Like so previously it looks like the plane antenna with the aperture like this one, and if they extend the y-axis, for example, we further, it's much longer. When we come back to here, then we're gonna, if we increase Ly, right, increase it, that means this, the beam width of this part gonna decrease. So when we come back to the taper reflector, use like reflector. This one, and this is Lx, this side is Ly length. So looks like this one, and when we come back to the what its radiation pattern. It's expressed as the theta x, theta equals roughly equals. This is reflector. Pattern. So it's roughly around lambda over Lx, and this theta y theta is roughly around lambda over Ly. So the this is a roughness expressions, the actual or the exact values for this one. When we wanted to calculate this, cos theta x theta equals the kx times lambda over Lx, the exact value, and the kx is a constant related to the stiffness of the taper. So for what? If there is no taper, kx equals 0, and if it has taper, and typically kx equals 1. If kx equals 0, there's no taper. If kx equals 2, it is highly taped. So typically equals 1. So it's roughly this way. So here, after the what? After the reflection of these tapers, the beam base is much larger, wider than that one, because the Lx, due to the green, Lx is much smaller. So this part is much higher, and this one. So that means what we want to see here is when we look at this part, because there is side lobes, it's only minus 13.2 dB. All right. If we wanted to suppress this part, that means we add upper stiffness and increase it. So that means this part is going to be suppressed, and the beam width becomes much wider. Becomes with a lower thickness, like so. Tapered distribution provides pattern with low side lobes. But the when low becomes wide. So from here we can see that there is a trade-off, right, between the side lobe and the beam width. If one lobe get a lower side lobe, that means the beam width will be wider, and oppositely, and the same thing also. So the directivity D is related to 4 pi over the beam width. And because as for the Hall antennas or the dish antennas. So it can also be related to the effective actor from the physical actor, right? So it becomes around 4 pi E divided by 11 squared. So this equation. And the physical actor equals Lx times Ly, right? So yeah. So for the that means for as the first order approximation, the effective area of the actor can be roughly equals to the physical actor. This is for technical rough approximation. So until now, we just demonstrated on the illumination, the uniform field illumination for perpendicular, rectangular aperture, and now we're going to introduce it via circular aperture, so which is more commonly used for us. With uniform illumination. So for a circular polarization, for a circular aperture, we not choose the Cartesian coordinate system. We're going to use the polar coordinate system. First, we set it like represented still in the Cartesian coordinate system. XA, YA, and XA. We use a subscript 8 means it's represented to an actor, and this is beta A, this is YA. And we also chose the polar coordinate system, and which represent the spherical coordinate system. All right, so the point R represent to the elevation angle theta, and also related to the so as shadow on the x-axis related to the Zimi's angle. So this is YA. So for a transformation from a polar coordinate to the Cartesian coordinate related to the RA, for example, RA means the radius expressed in the x or y plane. All right. So this is RA. A times cosine phi. This is RA times sin phi A. So then you can get the form factor H theta phi can be represented by A RA just in the x or y plane for representation for calculation. So it times the exponential component, right? So it's J RA and sin theta times cosine phi sin A plus sin phi, and also the d RA d phi A theta. So here's this one is R is from 0 to infinity, phi is from 0 to pi. This one. And so let's simplify it. This term represents the cosine phi or minus phi, right? So, and this part can be simplified to what? Because as the phi is from 0 to pi, so it is symmetric, alright? So that means finally the h only depends on the theta instead of phi. And finally we can simplify it to be pi times 0 to infinity RA times general pi RA sin theta and RA d RA. So because it is symmetric over the phi A axis, so we can also use this part to represent the formula part, because this is general is zeroth order Bessel function. And it can be represented by J node, for example, J node x equals pi 0 to pi infinity times e to x theta minus theta prime and d theta prime, something like this one. So this is the Bessel function. Can we simplify like such a condition here? And so when we look at this part, chi times RA sin theta, which corresponds to the rectangular aperture, it looks like chi times the Lx, alright? Lx times sin theta, alright? For the rectangular aperture, like what? Like this one, right? So because lambda or pi over lambda represented to the number px, right? So px times Lx, the aperture or the dimension, and times the sin theta. So for the circular aperture, also the same thing. So it looks like this one. So that means as radiation pattern is also almost like the previous one. It's something like this part, like this again. Also, and we also need to calculate, but the only different thing is the beam width, and it's for the half power beam width or half power angle and the nav angle, and this is the difference. So this is for the uniform illumination, and as we previously said that for the uniform illumination, its beam width it surely has the narrowest possible beam width for the main lobe. Okay, that's for the main lobe. But as side lobe, the power is side lobe, is a bit higher. It's too high. And for such a condition, especially for the remote sensing, such a difference usually is not enough for us for the detection. So it's going to reduce the resolution of the detection system, of the sensing system. So how about let's think method to reduce the power level of the side lobes. The first thing is to basically use the uniform illumination. So here you can consider the non-uniform illumination. So for the non-uniform illumination, that means the factor EA is not equal to a constant over the whole picture, alright? So it can be expressed as maybe it varies along the x-axis, also over the y-axis, but here we just consider it as the x-axis, and we assume over the y-axis as unit, so to simplify our analysis. So x-axis, this one, and x8 times 2 y8. So this one equals 1, so 1 x8. And so if we wanted to introduce, of course it has the x-axis, the variation variable xa, and also it has the variable theta, right? So in the polar system, our polar coordinate, so we transfer it to new variables. One is x1, another is u1. x1 equals to or x times xa, and u2 equals pi Lx over lambda times sinus theta. So we use two examples to simplify why we just such a transform, because we wanted to simplify our inductions on the form factor h theta. So finally, h theta equals half minus 1 to 1. So this is e1 x1 times u1 x1 x1. So this is simplifying this equation. Okay, and here our aim is to reduce the side lobe level, alright? Reduce the side lobe level, lobes, or the side lobes, side lobe area, side lobe level, this one. And so first thing is of course it is non-uniform. So the E1, X1 can have several kinds of distribution, follow several kinds of distribution functions. For example, it can follow a cosine function, and also it can follow, for example, a parabolic function. It can also follow a triangular function. That's all right. So the cosine function. That's a parabolic function. And also a triangular function. This one. So when we substitute these equations inside here, and we take the plots, we can obtain the beam width and the radiation, the radiation directivity, and the side lobe level also. So first, let's take this plot as an example, the cosine function. So for the cosine function, and x1 has order, we give us more choices. So n, it can be, of course, 1 to through integral, right? So that means its relativity d, and as side lobe level. Okay, let's simplify it. And also the half power beamwidth. So when n equals 1, 2, 3, 4. Is, for example, let's guess. When n increases, that means what? N increases, that means its period increases also, right? So increases, that means as half power beamwidth gonna be increased also. So that means when we look at this half power beamwidth, previously when there is the n equals no, for example, equals no, that means this part equals 1 as a uniform distribution, right? Becomes uniform distribution as beamwidth is 0.88 lambda over Lx. Alright? So for n equals 1, it becomes the same function. As beamwidth becomes wider. But, and this one is third one to the side lobe level. And when n equals 1, it becomes is the rate naturally, and with the sacrifice of the beamwidth. And further, when we increase the order to 2, it becomes 32. To 3, it becomes 40. To 4, it becomes 48. I will not show the plot, and I think you can try to plot it by using code program to plot this plot. And this is 1.5 over Lx. So wider again 6.6 and 1.94 also. And this directivity also going to be decreased. This one is 1. And when n equals 1, 81, 867, 858, 852. So for static condition, for when we set a non-uniform distribution illumination, when we wanted to increase, the side lobe level, increasing the side lobe level, gonna lead to the increasing of beamwidth and also the decreasing of the directivity, right? Both are related, all right? Or the wider beamwidth means a smaller directivity. So this is the sacrifice on static condition. let's take a short break. We can come back. Continue. Okay, let's continue. So now when we look at F for a uniform distribution is the beam base, for example, x1, x beta equals 0.0888 lambda over Lx, right? So F for a rectangular, for example, aperture, so the beta y theta is in right, 8 lambda over Lx. But for the cosine tapered aperture, so the beta x beta equals 1.2 lambda over Lx, and the beta y beta equals 8 L1. So when we come back to the calculations of the directivity, for example, the directivity is the this chart, right? So it's related to the beta x, beta and y beta. It's related to beta x, beta, y beta. So that means the directivity of that gonna be decreased more significant, right? So, for example, for the 0. For this part, that's 1 over 0.88 square, and this one becomes 1.2 square. So this is the reduction of that part is much more than that one. That's because it's the three-dimensional radiation pattern. So, if the beam width is reduced and all the side lobe level is reduced, it's gonna relate it to the another parameter is the beam efficiency. So first, let's take a simple expressions. Let's assume for a rectangular aperture, and its dimension on x-axis and equals dimension on y-axis equals a constant error. An arrow is around several wavelengths. So several wavelengths is round. So, and we can maybe M. M is around several values. So now let's take the plot on that one. So, for example, for the uniform distribution, it looks like it's narrow, right? The main lobe is very narrow. This one, and it has side lobes. This one. This one, so lower part. This is for the uniform, and for the sine cosine taper, and with n equals 1, n equals 1, then we know that. It's also normalized. It's 0 dB. So it's normalized. But its beam width is wider than that one, right? but its side lobes is much lower. This one, this one. So this is the cosine part. With then it equals 1. So for the if we want to get the big efficiency, that means we need a representation for that one, or an expression for that one. As we use theta b, the beam efficiency, it equals. So for beam efficiency, what we mean is we want to get the power in main lobe, power inside of the main lobe. So power radiated E with half angle theta 1 theta. It's related. Actually, the x-axis is gamma, right? Related to Lx over lambda sin theta. So this is really important. Divided by the total power radiated in the 4 pi solid angle. That means over the whole angles of the radiation pattern, and it can be expressed as for the whole angle. That means the theta phi, alright, the normalized intensity times integration d theta d phi, solid angle, and for the theta, the elevation angle is from 0 to pi, right? For the limit angle is 0 to pi, right? So this side, the denominator, is f theta phi sin theta d phi. So theta should change from 0 to theta 1, alright? For the first now angle. And phi is equal from 0 to pi again. So it can be expressed like this. It's related to the solid angle, right? This solid angle is the pattern solid angle, and this is related solid angle of the main beam solid angle. Sorry. So omega n represent low solid angle beam. And omega p is the pattern solid angle. So it's related to that one respectively. And so for this part, when we chose theta 1, for example, this is gamma, right? When we choose gamma 1 equals 1, so this is gamma equals 1, and this gamma related to 1.5 example. And so that means for the uniform illumination, the theta 1 equals uniform. lambda over L, right? This one is this one, for example. And because theta is a small angle, so sin theta can be related to theta. It's related to this one. And Lx equals Ly equals L. And for the non-uniform, one, non-uniform. Theta 1c is related to 1.5 for the tapered aperture. It becomes, this one becomes 1.5. So theta equals 1.5 lambda over L. So this is the synthetic aperture n equals 1. So let's assume if, so let's see how the beam efficiency is improved when we change the uniform illumination to the non-uniform illumination. So let's assume that okay, let's assume error, because error should be several numbers of wavelengths around this task. For example, it's 10 times lambda. So for error equals 10 lambda, that means then theta 1. Theta 1 equals 1 over 10, right? So it equals 0.1 RBD. And theta 1 say equals 0.15 RBD. Alright? So when we substitute these equations into this part, take the integration. So for this part, that means eta is around 80%. So that means the radiated power, 80% of the radiated power is contained, is inside of the, is carried by the main lobe. And for this part, it's related to eta equals calculation 93%. So that means 93% of the radiated energy is contained this main. And this is just for n equals 1, right? So when we increase n to equals 2, for example, and the rate generated eta becomes 98%. So it becomes wide, but almost all the energy, the radiated energy, is contained in main beam. And so what we want to see here is the application of the steep illumination or uniform illumination. Tapers can raise the beam efficiency or improve the beam efficiency when we increase n number to 3, 10, 4, 5, and it's grown around to 100%. Okay, 100%. But sacrifice of what? at the sacrifice of what? The beam width and directivity. So, how could we, for example, find a method we can improve the beam width? Also, improve the beam width, the directivity, also improve the beam efficiency. So, we want to design another kind of antenna arrays. Right. So, for the antenna arrays, the antennas can be organized with antennas, right? The whole antennas, the dipoles, the slots, and the parabolic dishes, and of course they will be used for this. And it can have several kinds of configurations, right? And it can be mostly used as the line and the link, right? So kind of two configurations, and for the line, it should be a straight line. For the plane, it can be, for example, a flat plane or a circular plane, something like that. So, and for this configuration, we first we need to consider as the radiation from each element. For example, it has several kinds of elements. We first consider, for example, one element, and for example, the element I. Its electric field can be one isolated element. Its electric field can be expressed as, or the element is in the spherical coordinate system, it's expressed as spherical wave, right? Times R, again, spherical wave. And also this is the element electric field. Electric field. And also another part. So this is the propagation factor, right? As we mentioned at the beginning. From this propagation factor, we can recognize whether the it is plane wave or spherical wave, something like that. And then also there is another factor. F theta phi, which is defines the direction. So this is the definitely defines the direction of this element, the electric field. So that means here for the element electric field, it has two parts. The first part is the amplitude related propagation factor, also the direction related or dependence. It usually depends on the it's controlled by the for example the phase component, right? So for the element, for example, I, if there is an observation point at Q, this point Q, what we really used, all right? So let's take a picture on edge. So there is a ray, like we have the first element at the origin of the Cartesian coordinate system. This is Y, and this is theta. So this is element, another element, and there are many elements which. So this is element node. One element n-1 element n. We have n number of the antenna elements. So the observation point is Q. So the so this is the distance R node R1, right? R n-1 R n, the distance to it. So we can define the far zone field for the element 1. Due to the element 1, we call it EI. Due to element I, it's RI theta phi. Can be expressed as the propagation factor, right? So E minus J K RI times direction factor theta phi. Here we assume all these elements, they have the same direction factor. So FE, call it FE. And because for each element, it has a fading coefficient. So we call it AI, fading coefficient. And the fading coefficient also is complex. So AI can be expressed as AI times sine I. This parameter represents the fading coefficient. It has an amplitude and also has a phase. So, if we have n elements, so the total field observed by the observation point Q. Here, the course for the far field region, we can assume the distance. This part is because it varies from node to capital N. So here we assume we can take the whole part as one antenna, and we assume its distances are node for this part, theta and phi. It can be expressed as I equals 0 to capital N times okay, now it's because it's from 0, it becomes n plus 1, right? N plus 1, n. So yeah, so n. So okay. EI, RI, theta, phi, right? And because we assume that all antennas, their directional factor is identical, so it can be calculated like was denoted n as AI, RI, number is KRI. So it's identical for each element. It's expressed by this equation. So because for the far field region, the R node is much larger than. So we assume the distance between each element is L, and they are have the same separation L. R node is much larger than 2 L square over lambda, right? So, and okay, follow. So assume it as D, not error. So error is the total distance, the total length error. So error equals n times D, right? So it equals 2n square d square over lambda. Like this. So for the Ri, we can see that it changes, right? It changes. Because for H1, Ri can be expressed as R node time minus right? R node is the the longest theta I. Theta I. This is theta. Cosine theta. Theta I times cosine theta. And so theta I means it's R node minus theta I equals, because the separation is SD, alright? So the first one is 1D, the second element is 2D, the third element is 3D, alright? So the ith element is ID. So I is an integral, not the represent for an imaginary part of that. So cosine theta. So this equation becomes sigma node n I R node minus ID cosine theta by the E minus J R node minus ID cosine theta times F theta phi, right? So here, because the R node is much larger for the far field zone, it's much larger than the 2n squared d squared divided by lambda, and it could also much larger than this part, right? So here's cosine theta. So that means we neglected like this way, and also for this part, it's also a constant. It's not the element dependent. So it can then be simplified as these two parts can be moved outside LH R node E minus J R node, and the inside LH is just this part. So now, when we take here we get the expressions for the electric field. We can also obtain the power density. So the power density as R node theta phi cos E node theta phi epsilon square. So it can be equals the 1/2 eta node f e theta phi square, right? This part square, and also we have Arnold square. Come back to here. So look at this one, Arnold square, fe f square. This part is disappeared. So and also this part, the square of this part, so values. So this one, sigma pi is noted. Then ai e j I d cosine theta, and the times last one sk I k d cosine theta square. So then look at this part. Look, all the elements have the same values, and this part is constant, or is power density of energy radiated by what? This one is by what? Come back. This one, right? That's the equals to each node the square of this part. Square equals to each node r square f theta phi square, right? So this is the, for each element, the element electric field related to the power density. So that means this one is also the power density of the energy radiated by individual element. Then we have another part as this part. Alright? So this part is for each element. They have their individual radiation, and this part should be the integration of them, right? So it is called array vector. So when we look at this part for the array factor, you can see it's related to what? When we look at this equation. It's related to first the exponential part as the distance between two elements, and also the angle related to the observation point, right? So it's related to the what? It's related to the individual elements, right? Also individual elements, and also AI. AI is what? The fading coefficient. So that means the array factor is affected by the individual elements. It's what? It's position, right? Position of individual elements, and also the fading coefficients for the elements also. but it would not depend on the what? It would not depend on the radiation. Oh, sorry. So for this part is the radiation pattern of for each element. So it's not related to this part. So which means the array factor is independent of the specification of the antenna. It just depends on the position of the elements and also the fading coefficient. It's not an antenna-specific parameter. And if we want to find a factor or a parameter to represent the array factor, so for any factor here, we can set a parameter represented for use f a theta to represent the array factor, which means the expressions for this equation can be simplified as pattern of each element or individual element times the array factor h. So it looks like the same as the previously when we want to try to conduct the expressions for the power density of single antenna, right? Means the S max times the normalized intensity, right? Like this one. So for the arrays, antenna arrays, it's also the same form, even though the expressions for each parameter are different. This one. So this one is this equation. It demonstrates the pattern multiplication principles. So it helps us to figure out the power densities of the antenna arrays by computing the Fourier power pattern and multiply the array factor together, and then you can get all these things. And now, if because here, as we know that the array factor Fa theta is expressed as I equals noted n and AI, right, times E J I K D cosine theta squared. So AI it equals small case AI times the base part, this one. So that means the array amplitude distribution, we call this one from the amplitude. And this is the phi I related to the phase. So that means the array factor is governed by the array amplitude distribution and the array phase distribution. So this is the array factors determined by these two kinds of distributions. So the amplitude distribution tries to control
this angle line?
Excuse me?
Oh, angle line. Imaginary part.
This is related to the radiation pattern. Yeah. And this part is related to as the used to steer the beam direction. So, if we take this further, for an example, we have n elements, and we want to calculate n element array, and for each one, they have the uniform phase distribution. Array with uniform phase distribution. That's and then that means previously uniform phase distribution. So it's a constant. So then F8 equals, it can be simplified to sine node square root times I node n and I e j I k d cosine theta square. That's this one, right? And this part, because it's imaginary, so it equals 1. So this period comes like this one, and we assume kd cosine theta is related to the phase difference between each element, right? So it can be used gamma to express that, and it also equals 2 pi d or lambda cosine theta. So it's wavelength related, and it can also be, this part can also be simplified as I equals node to n, and big I times e j I gamma square. Alright, so when we simplify it to this part, I think it is more convenient for us to obtain the impedance based on this one, and it's related to what? Related to the previous uniform electric field, something like here. A little bit more convenient for us to plot the pattern. Okay. So when we express it like this one, then we can do more calculations. For example, if we want to get, for example, we set the amplitude distribution AI is also always equal 1. Or 1. And this part is equal to n I gamma square. And when we take the integral the addition of all these elements together, and we can get the final expressions, it also follows a sinc function. And then the radiation pattern is going to be a little bit like the uniform distribution of a single antenna. And we're going to introduce this part and introduce the details on Wednesday at the same time. Okay? So see you guys on Wednesday. Yeah.
So you think the parties